622.12 lab 3 circuits. Purpose, predict behavior with series and parallel resistors, measure current and potential with ammeters, and learn about resistors and capacitors. Fundamental principles are node rule, loop rule, and Ohm's law. We build the model with materials given in the lab. You see the picture right here. Go ahead and mark me down for 100. Results, node and loop rule are proved. The current in an RC circuit is time dependent. All right, so we've also got some physics principles and equations used. The node rule, current in equals current out. So it's conservation of charge. Loop rule, a sum of all electric potential around a loop is zero. This is from energy conservation. Ohm's law, which is current through a conductor between 2 points, is directly proportional to the voltage across 2 points. Experimental design and assumptions. So here's the design they gave us. Here's it set up. You can see the 2 ammeters, the resistors, the battery, the light, whatever else you want. You can look at it if you really want to. So we're going to do loop rule here. R total equals resistance plus resistance, 147, because they're in series, so the total resistance is 147. So we know that the total thing is going to I1 is going to equal I2 because the total current's the same across the entire circuit. So we can just do V equals IR for the full resistance of the full circuit. V equals so I equals V divided by R. I equals 3 over 147. I1 should equal I2, and they're measured about 0.02, and the 3 over 147 is about that. So next, we're going to replace some of the ammeters with a voltmeter. And the voltmeter reads 3 volts because there's no other voltage drop, and the ammeter reads 0 amps because the voltmeter has super high resistance, becomes 0. I don't have a picture from my real lab, but this is what it technically should look like, whatever. Here's the calculation using the loop rule for the total charge over the time. We got the loop rule for the circuit here. VB equals IR 47 plus IR 100. So this is the ohms for each resistor. VB, you can see here is already 3 volts. We measured that in the previous slide. And then we're just going to add 47 over the amps, and we get negative 0.88. And we're going to look at F, and it's measured to be negative 2.1, and those are in volts. So now we're going to go and test the charge by replacing the voltmeter with an ammeter in parallel with a 100 ohm resistor. Now, something really cool happens here. The ammeter actually has really low resistance, so current passes through the ammeter instead of the resistor. The current takes it past the least resistance. This lowers the total resistance to only 47 ohms. So, now for V equals IR, we're just going to do VB equals IR 47. This means that I equals 0.06. The reading on the IRL lab was actually about 0.056, so kind of close. Next, we're going to, sorry, I'm going to drop the act now. Thanks, Professor Goldman, for having a cool voice to mimic. Now we're going to use V equals IR, or R equals VI, to calculate each resistant for each of the circuit elements. R47 equals 0.08 volts over 0.2 amps, 47 ohms, whatever. R100 should equal 100 ohms, so 2.1 over 0.02, about 100 ohms. The wire, the 0 volts, technically 0, not actually 0. We'll get that later. Same with their ammeter. We're counting it as 0, but it's not really 0. There's probably some resistance in there. As for the charging and discharging of the capacitor, we saw it took about 4 seconds for the bulb to go out. Then it started to get pretty bright, and then got dimmer throughout the duration. This shows an exponential decay over time, showing time dependence in an RC circuit. So the possible sources of error: human error in stopping and starting the stopwatch on time, and also charging the capacitor. I don't know exactly when the capacitor is charged. Do you? No, because you can't see it, so, kind of guesswork there, some human error. So, some people's might have gone 6 seconds, some people's might have gone 10. Mine went 3 or 4, whatever. Also, the wire and the multimeters have unknown resistances because it wasn't given, so, our numbers are all messed up. Discussion: what does the ammeter change? So, the ammeter does have resistance, so it changes the total current. As I just said, that's a possible source of error. What if we assume that there was no resistor? Well, the battery and the capacitor would charge instantly and also discharge instantly. Uh, be a nice little short circuit and cause a lot of flames to happen. Anyways, node and loop rule are true, and then I forgot to include this, but current and RC circuit is time dependent. Thanks.